All right. Hello, everyone. Can anyone hear me? Hello, 61C. I'm going to be stepping in for Kirsta today. And today we're going to talk about operating systems. But before we do that, let's take a step back and look what we've learned in 61C so far. So we started off with C, and we looked at how you can take a high-level program, and we also looked at how you can take these programs and compile them into MIPS assembly, which is what you did in your project 1, so you learned how a linker works. And then we looked at how CPUs work and how you can run your program on a CPU. And that's what you did in your project 2. We also looked at how caches work, how your CPU accesses memory, and how basically this entire cycle worked from starting a program on your CPU, fetching instructions, executing them, and accessing memory while you're executing, and then giving you a result. And you labs, you had a chance to try that out in a simulator. Now, while this is actually a full computer, it still seems a little bit different than what most people brought with you to class today. And why is that? Well, the main difference is really that the computers that you have here have a few things that our lone CPU and the Mars simulator didn't have. For example, they have a screen, and they have a keyboard, and they have storage. But the thing is, those are pretty much the only things that are missing. Well, and a few other things that, are in the details. But what do we need to change to the things we've learned so far in order to actually give us a full computer? And the answer is, well, we just have to add these things, the parts of the system that communicate with you, which is called the input-output or I/O subsystem. And this is actually slightly simpler than you would first think, and we go a bit more into details today. But essentially, you're taking these components, you're connecting them to your CPU, and you have a full computer. And if you don't believe me, you can go to Amazon, and you can buy one of these guys. This is called a Raspberry Pi. It's a computer in a credit card format. It costs $40, and it has all these components we've seen in this course. So you have a CPU, and in fact, this is actually the CPU, the caches, and even the memory all on a single chip. So the memory is actually stacked on top of the CPU. It also has a couple of other components like a graphics processor and so on, but essentially this is the CPU and cache hierarchy and so on that we've seen in lecture. And then everything else is I/O. So for example, you have an HDMI port that can connect to your screen. You have a couple of USB ports that you can use to connect a keyboard or a mouse. You have an Ethernet port to connect to a network. And finally, you have a mini SD slot that you have for storage where you can store files and so on. And this is a real computer. If you don't believe me, it runs Quake. So you can buy this thing, you can hook it up to your TV, and you can run Quake on it. But you're going to say, okay, but wait, when I run Mars, this is nothing like that. Because when I start my computer, I get this nice operating system. I have like a desktop. I can run applications. I can do all kinds of things. And when I do Mars, it just jumps into a program, executes, then prints out a number. And the difference between that and a full system like this is really just in the software. When I say just in the software, it's just like, well, there's actually quite a lot to the software. So the software I'm talking about is the operating system, which is perhaps the largest piece of software on your machine. So I found this infographic on the web, which is based on guesstimates, so I would take these numbers with a grain of salt. But what they're basically saying is they're comparing the numbers of lines of code in different software packages. And if you look at it, you have Windows Vista up here with like 50 million, and then this is Debian, so Linux with like almost 70 million, Mac OS X with 80 million. And in comparison, this is the number of base pairs in a mouse. So we're like 3/4 there almost in terms of complexity in your system. So the OS is really what holds your entire system together. And it is a very large piece of software that basically makes your computer what it is when you use it. So what does the operating system actually do? Well, the operating system is one of the first things that runs when you power on your computer. So there are a couple of earlier steps that happen that we're going to talk about later today. But essentially, when you switch on your computer and it goes through the first stages of booting up, it gets you into the operating system. And then the operating system's main job is to load, run, and manage other applications. So, for example, it's responsible for running multiple applications at the same time. So you can run a browser, and you can run, an audio player in the background, and all kinds of things. It's also responsible for isolating these programs from each other so that For example, a malware or virus can't harm any of the other applications running on your machine, at least in theory. And finally, it's responsible for multiplexing resources between applications. So for example, when you have Spotify and when you have a browser, they all want to access the network to go to the internet. The operating system has to mediate between those things. The operating system is also responsible of providing various different services. So for example, most operating systems will provide you with a file system service, which gives you folders and files and organizing things. It will also provide you with all the code that's necessary to communicate over the network. So there are protocols running that can get quite complex. And a whole lot of other services also related to graphics processing and so on. That's all within your operating system. And finally, the operating system is responsible to actually make all these devices that we saw earlier available to your applications. It's responsible for managing all your output to the screen. It's responsible for managing access to your keyboard, for example, or any other devices that you've connected to your machine. And it does so by using small applications called device drivers, which we'll briefly talk about today as well. So in today's lecture, we're basically going to briefly go into all these different aspects in detail. We're going to start with how you actually access external devices from an application. We're then going to look at the basic operation of an operating system, what happens when you switch on your machine, what does the operating system do. We'll then look how the operating system allows you to share a single machine, a single processor between multiple applications. And finally, we're going to talk a little bit about how it manages memory, which will also be covered a little bit more in future lectures. So let's start with devices. How does I/O actually work in a system? So let's start with the kind of application we've seen running on our CPU. Imagine you're in Mars, you have a MIPS application, and now you want to actually start accessing devices that are connected to your machine, devices like your mouse, your keyboard, your screen. So in order to do that, you need some kind of interface that exposes these devices to you. And that interface needs to do a couple of things. So one thing it has to do is it needs to be able to connect you to many types of different devices. There's so many different things you could connect to your computer. It's not just simple things like a keyboard. It's also you have so many different kinds of storage. You might have a flash drive, an external hard drive, internal hard drive, flash cards. These are all different devices, but you want to give the same view because you want them all to look the same to the application. Your interface also has to control these devices. So for example, it has to tell them what to do. If you have a printer, for example, the system has to tell it what to do, when to print, when to cancel a job, things like that. And you also have to present all these things to an application in a way that is actually easy for the programmer to use. Because as a programmer, you actually have to interact with devices quite a lot. And the first attempt that you might take at designing such an interface is to say, well, let's extend the ISA. And this has been done for some systems in the past. So you can say, what does a processor actually need to do to communicate with I/O devices? Well, it has to do two types of things. It has to be able to get input from the device and has to be able to output data to the device. And these are essentially just the same as reading a sequence of bytes from somewhere and writing a sequence of bytes from to somewhere. So for example, if you have a keyboard, you can imagine that keyboard just producing a sequence of characters and you just read them from somewhere. And if you have a screen that shows a terminal, well, you can just imagine just writing a sequence of characters that will be displayed in that terminal. So one way to implement that would be that you could have additional instructions in your ISA that do that I/O for you. So for example, you could have an instruction that sends bytes to a device and an instruction that receives bytes from a device. However, in some way, that is slightly duplicate with what we already have, because we already know an operation that reads, and we know an operation that writes, because this is the same thing that we do when we access memory. When we load from memory, we read a sequence of bytes. When we write to memory, we write a sequence of bytes. So this leads to another way of implementing I/O, which is popular in a lot of systems today, which is called memory-mapped I/O. And memory-mapped I/O basically takes the memory interface that you already have, that you're accessing with load and store instructions, and uses that for devices as well. So the way it works is that you take your address space, all the address that you can access in your program, and you say that a part of it now belongs to a certain device. So for example, you can say, we have a keyboard, and all the addresses from FFFF0000 to FFFFFFF now belong to the keyboard. So when I write or read from those addresses, it means it won't actually go to memory, it will communicate with that device. And in hardware, you can set it up such that there is a check before you go to memory that those addresses are actually forwarded to the device rather than to the memory directly. And the way you could use that to implement I/O is that you divide that section into different parts. Mainly there is a control part and a data part. And by writing and reading to these different portions of memory, you can actually control the device. So we'll look at how that exactly works in a second. So imagine you have a keyboard and you access it by reading from a certain part of memory. Now, you could just always basically have your CPU sit there and look at that part in memory, and whenever there's new data arriving, you do something with that data. But the problem is that you might have different devices. So how do you access multiple ones of them? And one way to do that is what's called polling I/O, which we'll go into in a second. So imagine you have your processor and you have a bunch of different devices, and your processor can read bytes and write bytes to those devices. And these devices produce and read data at differing rates. So for example, if you have a hard drive, say you have a flash drive connected through Thunderbolt, that will probably actually support a very high speed of data to access. So for example, Thunderbolt supports 10 gigabits per second. So you can imagine that some device might actually consume data at that rate. And at the other end of the spectrum, you might have your keyboard, where most of the time you don't have anything until the user presses a key. Then you get a byte of the key that was just pressed, and then you can process that. So the question is, how can we actually, as a processor, access all these devices? And the idea is that we go through these devices in sequence, and for each device, check, does this device have any data for us available? Can we do anything? And the way that works is that in this control section of the memory space that we reserve for this device, we install two words that act as registers that tell you whether the device is ready, so whether it has data or whether it is not. So one way to think about it is basically think about it like a flagman on a road, where you don't know whether you should go ahead and read from the device or write to the device or not, but the flag will tell you, yes, I'm ready, you can access, or no, you should not do anything. And basically what you do is you keep going through these different devices, you read these registers, and if the register says 1, which means that the device is available, you access it, and you do that by loading or storing to that data section in memory. Question?
Wait, is the control register just 1 bit or like a roll over?
It could be just 1 bit. In practice, it will probably have different options. So for example, you could have an option that tells you, that regulates the speed at which you access the device. But fundamentally, there's one ready bit that tells you I have data or I'm ready to access. And this process of checking that control register to see whether the device is ready, that is called polling. And so in code, it would look a bit like this. So imagine that you want to access a keyboard, and you would say, okay, let's pull the keyboard input to see until data is available. So we start by loading the address where we know the keyboard is, and then we load the control bit. And we check whether the control bit is 1, and if it is not, we go back to this loop and continue the same thing over again. And this allows us to basically say, let's look at the keyboard and wait until data is available. And once data is available, you basically read the data from a different address and then put it into a register in your CPU and you continue. So in this case, you would keep polling until data is available. So that gives you a way of saying, for example, I want to wait until someone has pressed a button on this keyboard. This is called synchronous I/O. You could also do it in such a way that you check, is data available? And if not, just return and try some other time. That would be called asynchronous. So you would basically just continue and check some other time. For output, you can actually do the same thing. So for output, this control bit would actually mean something different. It wouldn't mean I have data available. It means I'm ready to receive data. And the reason you need that is that you could otherwise easily overwhelm the device. So imagine, for example, you have a storage device that can only store a certain number of bytes per second. And if you exceed that number, you would have to drop bytes because you would overwhelm the device. This control bit would give you a way of saying, no, you have to wait before you send me more data. The way that works is very similar. You read the content of this control bit, load it into a register, you check whether it's 1, and if it's not 1, you go back to this loop and you continue until you actually are ready, and then you store it to that location. So this is how you can input or output to a device. Now the problem here is that polling can actually get quite expensive, and it depends very much on the device how expensive it actually gets. So let's assume we have a processor that has a 1 gigahertz clock rate, and whenever you do a polling operation, it takes you 400 clock cycles, which is the time that it takes you to call the polling function, access the device, check the control bit, access the data, and then return. So for different devices, what time of the processor time would you actually spend polling? And let's say you have a couple of different examples of devices. So here you have, for example, a mouse. A mouse you don't want to check that often because the state doesn't change that much. So if you change it, say, 30 times a second, that's probably enough. If you have a floppy disk, that's a very old example, but that one would, for example, transfer data in 2-byte blocks and would transfer it at a very low rate, so something like 50 kilobytes per second. So that would be an example where you need to actually poll more often, because instead of the mouse where you just check 30 times a second, here you actually need to poll for every data that you want to read. You can't miss any data that's coming from the floppy because that would be data that you need. And the same is true for a hard drive. So if you take this example of a hard drive which transfers data, say, in 16-byte chunks and transfers at 16 megabytes per second, which is a very old, very slow hard drive, would still mean that we can't miss any of these transfers. So we constantly have to check, is the data available, bring it into the processor, then check for the next data, is it available, bring it into the processor. So you can't actually just drop any of that data. So for these kind of examples, how long would it take us to actually poll for these events? And here's the example for the case of the mouse. So in the case of the mouse, we said we are polling 30 times per second, and each poll takes 400 clock cycles. That means that per second, we spend 12,000 clock cycles in polling. And that's not too bad, because 12,000 clock cycles in 1 second, well, we have 1 gigahertz, so that means we have 10 to the 9 clock cycles per second, so we only spend 0.0012% polling. That is reasonable, and that shows that if you have a device that actually you have to poll relatively rarely, it's perfectly fine to do this. But let's look at a different example. Let's look at the hard drive, and it's clicker time. So the question here is, let's take this example where you have the hard drive, which accesses 16-byte chunks at a rate of 16 megabytes per second. And you have to process all these chunks, and you still take 400 cycles to poll. So what percentage of time would you spend in polling now? Okay, I should okay, here we go. Oh, yeah. All right, since we're converging, let's have a look. All right. Quite a spread. Okay, so I give you another couple of minutes to talk to your neighbor. All right, let's have another look. Oh. Interesting. So the right answer is actually D. So let's do the math. So we have a transfer rate of 16 megabytes per second. And every time we poll, we bring in 16 bytes, which means we have to poll 1 million times per second. Each of these polls takes 400 clock cycles, so we spend 400 million clock cycles just polling. And 400 million out of a billion is 40%. And that's a lot of time just sitting there, spinning around and waiting for data to come in. So there must be a question.
The 16 bytes per poll, I guess, or 16.
This is coming from the 16 byte chunks. So whenever you poll,
You only poll a single byte at a time?
you pull 2 bytes. Yeah. Sorry, well, 16 bytes actually. Yeah. So one way to think about it is you have your control and data part of the address space. Whenever the control part says there's data available, it's going to be a 16 byte chunk of data that you can load from there. Any more questions?
Can you go back to the slide that said the technicians?
Yeah. So the key problem is that, one key problem is that every time you poll, you bring in a very small amount of data. But the bigger underlying problem is that maybe you shouldn't always be polling, because polling just means you basically waiting for data to arrive, whether there is any data or not. So wouldn't it be a better way if someone could just tell us if data is available without us having to explicitly ask every single time? And this is exactly what systems are doing a lot of the time today. So one analogy would be the following. Think about polling as picking up the phone every couple of seconds to see whether you got a call. Now, in this method, we're actually making the phone ring and only pick up if it actually rings. So the mechanism that you use for this is what's called interrupt-driven I/O. An interrupt is basically a kind of exception where you can interrupt the current execution of the program and jump into a function that handles whatever I/O you now have available. So there are a couple of pieces to this. The key part is that you add a table to your CPU that has a couple of addresses of functions to jump into if you receive certain interrupts. And then you also modify your CPU such that I/O devices can actually send an interrupt to the CPU, which will suspend your current execution and execute the corresponding function from that table. So let's take an example. Let's say you're running some program on your CPU. It is running on some stack. And you have a couple of different types of interrupts. And in your CPU, you have this table that says, for this type of interrupt, I have this handler, which is just a normal function somewhere in memory that you can jump into if you receive that interrupt. So say you're executing, and at some point, some device, for example, your keyboard says, oh, I have some new input. So what your CPU will do is it will interrupt that program wherever it is and basically do a jump and link to that function. So it will get this interrupt, will suspend the current execution of the program, will look up the handler for that interrupt, and jump into that code. Now that code is going to be executed on the same stack as your normal program, which is a little bit confusing because it means you have to be very, very careful to not damage the content of the stack. So you need to, for example, save anything, any registers and so on, as you execute your interrupt. And then that interrupt handler executes. For example, it puts that data that it just received into some memory locations that can be used later, or acts on it in some other way. And once it finishes, it goes back to the previous location in the program and just continues execution. So the important part here is that when you have an interrupt, the program that you're interrupting is actually not seeing it at all. You're basically jumping to this routine, executing it, returning to where you were before, but the program basically just doesn't see it. It will just think, I continued execution. If you measure time, say here and here, you would notice that this suddenly took longer than you were expecting, but that's the only thing that you see that you got interrupted at some point. And this is a very powerful and general mechanism that allows you to implement a whole lot of different kinds of I/O. So keyboards are one example, but also when you have a storage device where you send a request and it takes a long time to come back, you basically send off the request, and sometime in the future you will receive that interrupt back that says the data is now available, and only then do you process it. And that is much, much better than just sitting there and waiting for that request to finish without being able to actually do anything during that time. Any questions about interrupt-driven I/O? Yeah.
Is this only used on things like hard disks, or is it used for like mouses?
The question is whether this is only used on things like hard disks. It's actually used on a lot of things. I would say it's especially useful for devices that very rarely send requests. Like, for example, keyboards are a good example, because if you had a program running and you want a way to cancel it with a keystroke, then you don't want to check every once in a while whether there is a new keystroke. You want to react on an interrupt and then interrupt the program. All right, so we're about halfway through, so it's time for some administrativia. Project 3 is due on Sunday. So the goal is 3 kilohertz per second. And one thing I want to stress is make sure that your tests pass. This is quite dangerous, because if your tests don't pass, we have to give you 0 points, because the problem is that you can make your program arbitrarily fast by not doing anything. And that happens quite easily. So make sure you pass the tests. The 3 kilohertz per second are on make benchmark huge. So if you want to make sure that you get the performance you should, run make benchmark huge. We're going to grade your assignment on an isolated machine. So it's probably going to be slightly faster than you currently have it, because currently people are sharing the same machines. And you can make it much faster than 3 kilohertz per second. I really want to encourage you to take part in the competition. It should be great fun, and I'm really interested to see how fast people can make this. You can do much, much better than 3 kilohertz. Question? You should send me an email about that. That shouldn't be possible. Oh, the question was you can skip a lot of the cats and still pass all the tests. So I might be releasing some new tests if that's what's happening. Yeah. Question.
You're passing just the regular benchmark test. Would you expect there to be any problems in making each benchmark?
You mean, I think the question was whether there's any difference between the test and the benchmark?
Yes.
Yeah, so the tests are designed to capture a couple of things that the benchmarks don't. So the benchmark actually doesn't check for correctness. You can, if the benchmark completes, that doesn't mean the results are at all correct.
Well, actually, I meant the difference between the different sizes of benchmarks.
Oh.
If it passes the test on one side of the benchmark, would the other sizes should work?
Yeah, so everything should work. Yeah. Question. Sorry? There are no secret tests, but we might release more tests before the deadline. But I think that would happen by tomorrow. Yeah. But please do send me your code. I'd be interested in reproducing that. All right. So let's go back to operating systems. So now that we know how to use devices on our machine, let's look at the operating system itself. And let's first look at what happens when you actually switch on your computer. And in a way, what your computer does when you switch it on is actually very, very similar to what Mars does when you hit the run button. So Mars will basically just jump to a certain address in memory and execute whatever it finds there. And then will execute until you reach a certain point where it stops. And this is really all that Mars is doing. Now, your computer does exactly the same thing. So when you switch your computer on, what it will do is it will set the PC counter to some value and then read from that address in memory to execute the first instruction. But instead of that regular memory, that location will normally be a memory-mapped chip somewhere on your board that contains some code that's stored in there. That's called a ROM. And you often hear that described as the firmware or the BIOS. And it is basically just a tiny bit of code that's somewhere fixed on your hardware that you can load. And what that code does is will basically just load itself into actual memory and then jump to that location and then start booting up your machine. So this is kind of how your computer starts when you switch it on. It will load that data from that chip into your memory and jump into that function that was stored on the chip. Now, the code that it executes is called the BIOS, which is a very basic piece of code that knows how to talk to a couple of input-output devices and, for example, read some data, write some data from there. And it is responsible for initializing things like, for example, your hard drive or the screen and loading more data to execute. So what this BIOS will do is, for example, it will look at your hard drive, initialize it so that it can access it, and then load the first block that is stored on that hard drive into memory using the I/O routines. And that first block usually contains what's called a bootloader. A bootloader is another small piece of software that is responsible for loading an operating system. So the reason you need a bootloader is that the BIOS really doesn't understand the format of the data stored on the hard drive. It just knows I can read this block of data from the beginning of the hard drive, but for example, I don't understand what files or directories and so on are. The bootloader, on the other hand, actually does. So the bootloader is smart enough to access a hard drive, for example, find a certain directory, and find an executable file that contains the operating system. So what it will do is it will access your hard drive, load your operating system into some location in memory, and then jump into the entry function for that operating system, something equivalent to main, basically. And once it has done that, your operating system will actually go ahead and boot, initialize all its services, like the file system, the network. It will talk to different components in your machine to see what devices it actually has available, and initialize all these devices. It will load drivers, which enable it to actually manage devices. And once it has done this whole sequence of things, it will jump in what's called the init process. And the init process is just a normal program. And that is something like, for example, your desktop or just a terminal that you can type things into. And then that program will just run. So when you switch on your computer, that's basically what's happening. You're first reading that small bit of code from that ROM into memory. You execute it. That piece of code knows enough to access your hard drive, read the first block from your hard drive, which contains the bootloader. It loads it into memory, runs the bootloader. The bootloader loads the operating system from the hard drive, and then it jumps into the operating system and it runs. So this seems like quite a complicated sequence of things, but it is actually still the same thing as just accessing pieces of memory and jumping to different locations. It's just a normal program, just like what we've been doing in Mars all the time. And the thing is, when you run your, say, Mac, I see a lot of Macs here, the problem is you don't actually see any of these things happening. So about 10 years ago, you actually saw a message like, this is the BIOS, and then you saw this menu from the bootloader, and then you saw a lot of text messages when your operating system was loading. On a Mac, all of these things just show an Apple logo, so that it doesn't look quite as scary. But the funny thing is, actually, you can still see how it changes, because the tone of the background of the Apple logo actually differs between these different stages. So you switch your computer on, you have one color tone of the Apple logo, then it blinks and it looks slightly different. That's when it changed to the bootloader. Then it blinks, looks slightly different than when it's actually jumped into the operating system. So even on a Mac, you can see that sometimes. To show you that in practice, though, I'm going to actually run a virtual machine which does all these steps as well. So a virtual machine is basically just a full system simulator that is basically running a whole machine with real software within your machine. So this is Linux booted up at the moment. So I'm going to just hit reset, and this is the this is the BIOS, and the BIOS loads the bootloader, which is this one. So here we have the bootloader, which shows us this menu, which just tells us where should I actually load the operating system from. And in this case, we say, well, just load it from. This is a CD-ROM image that contains the operating system, so it says load it from there. So bootloader actually knows, for example, how to talk to a CD-ROM drive. And then you load it, and then it loaded the operating system, and now it's actually executing the operating system, which will initialize all the devices, all the different components, and so on, which is happening right now. And after a while, it finishes, and then just jumps into this shell, and you can just run all your commands. And this is literally everything that happens. You hit on your computer, it loads all these things, and then you end up in your shell, which is just an infinite loop, waiting for things coming in from the keyboard and acting on them. Okay, so now we're at this point. We've booted our operating system. We are in the shell process, which is just looping and waiting for user input. So how do we actually run programs? So programs are running in what's called a process, or at least it's called like that in most operating systems. And you can think of a process as a unit of managing one program. So one program is basically managed as one process. The way you create processes in Linux, just as one example, is that a process can fork itself, which means that it turns into two processes, and then one of these processes can load an application and jump into it. And the way it loads an application is just that you give it the name of the file of the application. So when you say something like ./CNN, it will know that there's a file called CNN that is containing your application binary. And that command will load that binary from the hard drive into memory. That binary has a table where it says the main function is at this address. And then it just jumps to that main function and executes it. And basically, that is all there is to running applications. Now, a problem is, of course, that if you just do that, the application basically can take over the entire machine and just do whatever it likes, because we just jumped into an application. and it is running on that machine. And you could, for example, just override the operating system and do whatever it likes with that machine. And in order to prevent that from happening, you have what is called a protection. You have a protection mechanism that's called supervisor mode. So the way this works is that your CPU has an extra bit which tells you whether you are in supervisor mode or in user mode. And supervisor mode is what your operating system runs in, where you have full control of the machine. You can run any instruction you like. You can access any part of memory you like. Whereas user mode is a limited set of features. So in user mode, for example, you can't access certain parts in memory. In user mode, you can't run certain instructions that are reserved for the supervisor mode. And the purpose behind that is that it allows you to constrain your application to a certain subset of functionality that keeps it under the control of the operating system. And one important limitation is that when you're in user mode, you actually can't change back into supervisor mode yourself. You only change back into supervisor mode if you get an interrupt. So what that means is that an operating system can keep control of your CPU at all times, for example, by installing a timer interrupt. So the way it would do that is that it tells some unit in the CPU, I'm giving the CPU to an application for, say, 10 milliseconds. And in 10 milliseconds, raise an interrupt so that it jumps back in my interrupt handler and I can get the CPU back from the application. And then it would jump to the application, jump into user mode. The application runs. After 10 milliseconds, you get an interrupt. It jumps back into supervisor mode, and the supervisor mode can say, okay, I want to run the application a bit more, and jump back into the application. Or it can say, no, I want to stop running this application. I'm just going to jump somewhere else. So this is a way that you can keep control of applications that are running. Now, I just mentioned that applications are actually limited in what they can do. And one of the limitations is that they can't just access any devices. And that's what you want, because you don't want your application to, for example, just take over your network, for example, or crash your computer by just snatching away all keyboard events and things like that. So if you're an application, how are you actually going to access devices? And how are you going to access operating system services such as the file system or the network? And the way you do that is through a mechanism called syscalls. And syscalls you've actually already seen in Mars. These were the things that you had to do when you, for example, wanted to write to the console in Mars or exit your application. So syscall is basically like a function call into the operating system. And the way they implement it is that for a syscall, you first put all the arguments to that function into registers that you need. And then you have a special instruction that raises what's called a software interrupt. And a software interrupt is basically like any other interrupt in that it jumps into the handler that's registered for that kind of interrupt and jumps out of supervisor mode. So by raising a software interrupt, you leave your current application and you jump into the handler that your operating system has registered. And that handler then can basically do whatever it needs to do to handle that syscall and afterwards jump back to the application. And you use that to implement basically any interaction between your application and the operating system, such as write to this file, read something from the keyboard, send something over the network. These are all implemented as syscalls. And one neat side effect of using syscalls for all these things is actually that the operating system can control the access of different applications to these different resources. So, for example, the operating system can say, I only want to give like 50% of the bandwidth to the hard drive to this application and 50% to this, so that you don't have one application that monopolizes this entire resource for itself. And you can all do that because all the syscalls are implemented under the operating system, and you have full control of what's happening there. Any questions about, yeah?
How is a syscall different from giving the program access to supervisor mode? Like, how does the OS know whether, if the syscall is asking to do something that's wrong?
So the question is how a syscall is different than just giving the application access to supervisor mode. So how do you maintain the protection? Is that the question? Yeah. So
The point of the supervisor mode is to keep it from doing certain things, then you then
Yeah, so the key difference is that if you gave the application access to everything that the OS has access to, it could do anything. It could override any part of memory, for example. Whereas if you only allow it to go through syscalls, the OS can check when a syscall gets executed whether the arguments it was given are actually something that the application is allowed to. So imagine, for example, that you have a syscall that could write some data into some location of memory. The operating system could perform a check at the beginning of that syscall whether that application is actually allowed to write to that part. Does that answer the question? Okay. Any other questions? All right, so let's look at how your operating system actually runs multiple applications. So when you have your Mac or whatever computer, it will run many different applications at the same time. And the thing is, you're normally running more applications than you have physical CPUs in your system. So you need to do something to actually share a single CPU between multiple applications. And the way you do that is that you don't actually run them at the same time. But what you do instead is you run each application for a little bit, then switch to another application, run that one for a little bit, and then switch back to the application you had before and run that one for a little bit. And that's called time sharing. And it's basically what almost all machines are doing today. And it's one of the key responsibilities of the operating system. So the way this works is that when you run a program, you install a timer interrupt, as in the example from before, and then you jump into that application and you just let the application run for whatever it wants within its permissions. But then at some point, say after like 10 milliseconds or 80 milliseconds or so, the timer interrupt will trigger. It will go back to the operating system, and now the operating system can decide whether it wants to continue running that application or run some other application. So if you're sharing your CPU between two different programs, what the operating system is probably going to do is that when you get that timer interrupt, it is going to switch the program we're just running out to the other one, so that each of these two programs gets to run 50% of the time. So how is that switching happening? Well, when you get that interrupt, you have to do what's called a context switch. A context switch basically means you change your system from one application to the other. The way that works is that within your interrupt, you take the current stack, all the different register values, and so on, and you put them into a data structure which you store somewhere. And then, in order to switch to the new application, you get that data structure of that application and restore all the things from there. So you're basically taking a snapshot of the current state of the application and then load the snapshot of the application you want to change to. So that allows you to basically switch back and forth between multiple applications running on the same CPU, with giving the application the impression that they're actually running for the whole time. The application actually doesn't notice that it ever was interrupted because, well, you restore it at exactly the same state it was before when you continue, so it, for the application, just looks like it's running and running and running. And that gives you the illusion as if you have multiple applications running on the same CPU, even though you're actually just switching between them very, very quickly. Any questions about this part? The question is whether there's a large performance penalty. So you normally choose the frequency at which you switch between applications such that the time it takes to switch is much, much lower than the time that you run. But it is true that when you have a lot of applications or you have to switch very, very quickly, this can actually become a performance bottleneck. And there are a lot of very latency-sensitive applications where actually this switching is causing problems. And so there's an entire area in operating systems research called scheduling, which just basically looks at how do you switch between applications most efficiently. And it's one of the oldest research areas probably in all of computer science, actually. Any additional questions? All right, so we're running all these different applications, and we basically give the illusion that they're all running in parallel. So what problems could this lead to? And one of the key aspects is that when you run multiple applications in parallel, you need to protect them from each other. So imagine, for example, that you have your web browser, which has your online banking application, and then you have a virus running at the same time. You don't want the virus to access your online banking application. So you need to have a way to isolate these different apps. And the problem is that the supervisor mode alone doesn't give you that power. The supervisor mode prevents you from taking control of the machine, but it doesn't prevent you from accessing another application's data. So we need a different mechanism here. And that mechanism is called virtual memory. So virtual memory is basically a mechanism by which you can give each process the illusion that it runs on its own on the entire machine and that it has the entire address space for itself. So if one application writes to address 1,000 and another application writes to address 1,000, they're actually not overriding each other. They have the impression they have the entire machine on their own, but in reality they're actually separated from each other. And that has a couple of advantages. So the isolation is probably the most important aspect because you need to protect the different applications from each other. But you also have this problem that for different applications, you need to decide where to put, for example, your code or your data in memory. So when you wrote your linker for Project 1, you remember that the linker decided that each code section, for example, goes into a certain fixed address in memory. But the problem is if you load multiple programs that want their code to be at the same address in memory, you can't do that if you don't have some kind of mechanism to isolate, to basically give each application its own view of the memory. And the final reason for using virtual memory is that it has been traditionally used for it. It also allows you to give you the illusion that you have more memory than you actually physically have. And that happens by transparently moving data between the hard drive and the memory, which is something we'll go into in a little bit more detail later in the class. So what does virtual memory actually mean? So if you just have a conventional processor, and it has these instruction caches, and it has your data cache, and these produce addresses that they send to memory and the caches and so on to get data, and those addresses are sent to DRAM, and then the data comes back and they go back into the caches. So those are called physical addresses because they tell you the actual address in the memory that's attached to your processor that you want to access. And in order to give each application the illusion that they have their own space, the first thing we need to do is that we need to actually replace these physical addresses by something called dynamic addresses. So a dynamic address is basically an address as the application sees it, and that address then has to be translated to a real physical address. So what motivated this in the beginning was that, well, you wanted multiple applications on the same machine. Back in the days, the key reason was that I/O was very, very slow compared to how fast your application was running. So you needed actually multiple applications to make use of your machine because you wanted to run your second application while your first application is waiting for its I/O. So people were trying to actually run multiple applications on the same machine, and they ran into these problems that you needed to protect them from each other, and they all needed to basically have their own addresses that they could access without interference. So what people did was that they split up the physical memory, and each application would get a different consecutive part of the physical memory. So say, for example, program 1 has the physical addresses from here to here, program 2 has the physical addresses from here to here, and then your S uses this part of the address space. And these would not overlap. And now every address within the program you would express relative to this space in memory. So you say, for example, address 1,000 is now not 1,000 from here, but it is 1,000 from the starting point of your program's address space. And that has two advantages. Now you're actually location independent, so you can have two programs that assume their code start at address 1,000. Doesn't matter because for this program the address 1,000 is here, for this program the address 1,000 is here, they don't overlap. And you also get that protection because you can say if program 2 tries to access something here, that is not within its range, so you know you can ban it from doing that. And in the end, it's the responsibility of the operating system to set all these things up. So when it loads the program, it has to say, okay, I give the program this part of memory and set up all the different hardware features to enable this to happen. So how would you implement this in hardware, actually? So you need some hardware support for this. Or some hardware support for this would be really good, because otherwise you would have to rewrite your program at runtime. So the way you implement that is that in your CPU, you add 2 additional registers, which represent your currently running program. And one of these registers is called the base, and one of these registers is called your bound. And whenever you load from a certain address, you take that address, which is your dynamic address or logical address, how it's also called, and you first add that to the base. So the base is the starting point of your program section. So now you get an address that is a physical address that tells you the actual location where you have to access your data. And then the second thing you need to do is you need to check that you're not accessing anything outside this region, and that's done using the bound register. So once you have this address, you also check, is it actually smaller than the bound? And if it is not, then you're actually trying to access a part of memory that you're not allowed to, and you can prevent that, for example, by raising an interrupt, which gives control back to the operating system. The operating system can say, wait, there's an application that did something it's not allowed to. I'm going to shut down that application. So this is a pretty simple mechanism to enable you to implement a system like this, where each program has a part of memory. It has the impression that it's running on its own because it can't ever access anything outside this part. And from the application's perspective, that part starts from 0 and goes to some upper bound, which are really the only addresses the application cares about, because these are the logical addresses that it sees.
What determines the upper bound? Is it the OS or the program itself?
So the question is, what determines the upper bound, the OS or the program itself? So most likely you are going to have a field in your binary that tells you how much space you will need. And the operating system can, for example, decide to give you more space or less space. You might also want to dynamically actually change this. So, for example, if you see that an application actually starts small and then needs more memory, you could also dynamically extend this. Question?
So then that means that you can only run a certain number of programs simultaneously, right? Like after a certain point, it's kind of off.
Yeah, that's right. So at some point, either your memory is going to be full, or you're going to run into a problem that's called fragmentation that we'll actually go into detail a bit later about. But this is so you might actually run into problems with this approach later, and we're going to show you how to actually do slightly better. So this is kind of a first approach, and this has actually been implemented in some real systems. In fact, a lot of the Cray vector supercomputers used to implement a scheme very similar to this, that is the same except that it has 2 base and bound registers, one for the data and one for the program. Can anyone see why that would be a good idea? That's true, yeah. So what you can do in this case is that multiple programs on the same machine can actually share their code. So for example, if you have library routines, you can put them into one place that you access from all the different applications at the same time, and that's protected with this program-based register and program-bound register. And then every program gets their own data segment. So once you put these things into the pipeline, it basically looks like this. It's actually quite fast. You only need to introduce an adder before you go to the instruction cache. You need to introduce an adder before you go to the data cache. And this is actually quite a cheap operation, because you need to do an addition anyways in order to get the address you're accessing, because you have your offset. So you just put another carry in there, and it's pretty much the same operation. So it is a very simple modification to your pipeline that gives you this dynamic addressing and that gives you protection. However, this mechanism is not perfect. And one key problem it suffers from is what's called memory fragmentation. So imagine you have 3 programs running. One is up here, one is up here, and one is up here. And then you have 2 more programs come in, one is being put into this part of memory and the other one here. And then say these two programs terminate, so now they leave. And the problem is that you end up with these small gaps that might be too small to actually fit any program in. So over time, these gaps will basically get smaller and smaller, and in the end you have all your programs spread across your address space in such a way that you can't fit any new programs in, even if you have enough memory, just because the gaps are becoming so small. So the way to get around that would be to actually physically move programs from one location to another from time to time. So for example, you would move everything to one end of the address space to free up a consecutive part of memory again to add new programs. But that is very expensive because you actually have to move data around in memory. And that is why fewer systems today actually implement base and bound, but instead you use a different approach which is called paged memory. So in paged memory what you do is that you take the address, the logical address that you're accessing, and you're dividing it into two parts. The lowest part of the address is called the offset, and the rest is called a page number. And that is a little bit like hash lines. So a way to think about it is you have basically a block of data, which is one page. So it could be something like 4 kilobytes, which is a common size. You have your lowest part of the address is your offset within that page, and then the rest tells you which page you want. And then what you can do is you can have a table that tells you where each part of your address space is actually going to in physical memory. So say you have a logical address space that has addresses from like 0 to, 16K. And then you have a table that tells you the first 4 kilobytes here are actually at this address in physical memory. The next 4 kilobytes are at this address in physical memory, and so on. So this solves the problem of fragmentation, because now your physical memory just has to hold these 4K chunks that are pages, and you can basically in this table just say, well, this one goes here and this one goes here, so they don't have to be consecutive. So if you have programs of different size, they're still divided into these 4K chunks, and you can arrange the 4K chunks whichever you want. So the gaps are always going to be multiples of 4K as well. Any questions about this? Yeah.
So then where's the page table itself?
Very good question. So the question was where's the page table stored? And the answer is it's stored in memory itself. And we'll actually look at how exactly that works in the last couple of minutes. So what you basically have is you have all these different processes. They all have their own address space. They have this impression that I have this large address space from address 0 to whatever I want. And then I have a table that tells you, well, these 4 kilobytes in the address space are actually in this physical location. These 4 kilobytes are in this physical location, and so on. And so you have one of these page tables for each process. And then in your processor, you basically have to look up the table, translate the address, and then go to the right location in physical memory. So this gets back to the question, where's that page table stored? And it is stored in memory itself, but there is a problem, which is that how big would the page table actually be? And if we just implemented it the naive way, if we just had a table where we say the first 4 kilobytes of the address space go to this location, the next 4 kilobytes go to this location, etc., it means that we need one address for each 4 kilobytes in the entire address space. So even if your program is if you have, say, 4 gigabytes of memory, and your application is only using, say, 10 megabytes of that, you would still need an entry for every single page in that 4 gigabyte space. And that is very wasteful. So what the okay. It seems I have rearranged my slides, or actually not rearranged, I dropped some slides. But what you're basically doing is you're you're storing the page table in a format that allows you to only store the pages that you actually need. And we will go into a little bit more detail for that in a future lecture. And so what do you need to do when you actually want to translate an address from a logical address that your application sees to the physical address in memory? Well, what you need to do is you need to go into memory, look at your page table, see where the page is located, add the offset to that, and that gives you your real address. And as we'll see later, that can actually get very expensive because now every memory access can actually turn into two. One to access the page table and one to do the actual memory access. And you actually get around that by adding an extra cache just for page table accesses, which is called a TLB, or Translation Look-Aside Buffer. So all this will be covered in the next lecture. So in conclusion, so what we've seen today was basically that once you have that basic machine that consists of your CPU and your I/O and all these different components, it's really all about the operating system. Once you have that machine, what you get to see is actually just whatever your operating system decides to do. However, there are a lot of things where your hardware can actually help your operating system, and virtual memory and interrupts are one example of that. There are a couple of other places as well. Now, there's a whole lot of interesting research and work in the area of operating systems, and if you're interested in that, I would recommend to take 162, which goes into a lot of detail and actually allow you to implement your own operating system, which is a lot of fun. And in 61C, the next things we're going to be talking about is go into a little bit more detail of both of these things. We talk more about virtual memory, how the page tables are actually structured, how TLBs work, and so on. And we'll also talk more about I/O, give you a couple more details of how interrupts and so on work, for example. And since we finished a little bit early, so I can take more questions as well, or also about the project if people are interested.
So if the page table breaks up like your memory accesses to like different parts, does that affect spatial locality?
That is a good question. So usually it doesn't, and the reason is that 4 kilobyte pages are large enough that it captures pretty much all spatial locality that you might have. Oh, the question was whether it affects spatial locality if you split up your memory into these pages. Any more questions? Sorry?
Is there ever fragmentation from freeing page tables themselves?
Oh, very good question. So the question was, is there fragmentation from page tables themselves? And the answer is, there is, but a different kind of fragmentation than we saw before. So before we saw these problems that you have these different regions, and you get these differently sized gaps between the regions. You don't get that with page tables, because all pages are 4 kilobytes, so all the gaps are multiples of 4 kilobytes as well. However, you have these problems where, for example, you're only using a few bytes within a page, but the rest of the page stays empty, and you can't do anything about that. And that's called internal fragmentation, and you get that with page tables, but it is more limited, because internal fragmentation is limited by the size of a page. You can't waste more than a page by doing that. Question?
I know operating systems like let the user manually set like the size of the page files, basically. So like, how does that affect performance? Like adding more or less size of the page, I guess?
So the question is, so operating systems today let you pick your page size, and it does affect performance actually quite significantly. It depends on your workload. So if you imagine you have you run programs that work on very, very large data sets. So say you have a program that has many, many gigabytes of data, then you don't want small pages because you spend a lot of time bringing in small pages, whereas you always want all the data available. But if you have a lot of very small programs running, for example, you want small pages. And it is usually a trade-off between the data set that you have and also pressure on your TLB. So if you have smaller pages, you have to store more entries in your TLB, so that cache that stores the translations. Yeah. All right, thank you, everyone. So I'll stick around. I stick around for questions if anyone wants to talk about Project 3. Seems we were much faster than expected, but.